Welcome back. So in this session, I'm going to give you a live demonstration on how to use ProCACD in kind of solving different problems and everything. So I'm going to take a simple example from our lecture, the control level problem of the tank, and we'll try to first kind of do the generic modeling in MOD, and then we will see how this model can be used to do different things using ProCACD. Okay, so first I'm gonna show you the generic modeling. So I'm gonna open my MOD. Okay, and then close everything else. So first thing, I'm gonna open a new one and try to save this as a text file. Yes, and so hope you remember the steps in kind of developing a model in MOD. The first and the foremost thing is to go to the model construction, and in the original model you just type in all your equations. Okay, so this is a tank model, and this is done by me. Okay, so let's start. So I'm gonna keep this one aside, and then yes, so here I'm gonna write the system equations in the format of the generic template. Okay, so I hope you remember that we need to keep certain suffixes, like the manipulated variable has to be ended with MV, and the control variable has to be ended by CV, and the binary variables for open loop is OL and closed loop is CL, etc. So first I'll write the first equation here. So it's the change of height with respect to time. Since this is a control variable, I'm going to add CV, and 1 is for one pair of CV and LB. Since there is only one pair, you can avoid it, but I would always suggest you to go with the same convention. So if you have multiple pairs, and if you're writing for the first pair, you always go with 1, and for the second pair, you always use 2, like that. Okay, so it is given by F in minus F out divided by the area, the cross-sectional area of the tank. Okay, now F out is given by alpha, but alpha is a manipulated variable, so I'm going to give MB1 at the end into square root of the height, which is h, and it's a control variable, so it's h. Okay, similarly the error between the set point and the actual height, error 1, is given by HCV1 minus HCV1 SP, okay, the set point, and DAE1, okay, so 1 equals to error 1. Okay, now this is the most important step, where you write your control equations. Okay, so I'm gonna write alpha 1 alpha MB1 equals to alpha MB1 into OL1. So here OL1 represents the binary variable for open loop. Okay, now all these are, whatever is inside the bracket is for the closed loop. So P1 I'll write for the proportional controller, P1 into, okay, error 1, okay, plus alpha MB1 star. Okay, this multiplied by the binary variable for closed loop proportional controller for MBCB pair 1. Okay, similarly we will write for proportional integral controller, okay, where P1 into error 1, okay, plus integral coefficient I1, okay, into, and then you multiply it with AE1, right, plus your alpha star. Okay, now you multiply it by the binary variable for closed loop, proportional integral for pair 1. Okay, similarly we will write for the PID. Okay, so P1 into error 1 plus integral I1 into your AE1, okay, plus your D1, which is your derivative coefficient, into your THCB1, okay, and followed by your alpha MB1 star. Now you should multiply this with your closed loop PID 1. Okay, now at the end this is for pair 1, right? So there is one more binary variable which is pair group 1. Okay, so this is the entire model, and hope you remember that you should translate it first in order to translate it to the language which is understood by MOT. Okay, and you should choose that compounds are not used in this model. Okay, so no need this anymore. Let's say, okay, so now we could easily see that the model has been translated, and the next thing is defining or classifying the variables. So I'm going to go here. I will choose all as parameters, most of the variables as parameters, except for the binary variables. I will choose them as no. So this is open loop, and this is, let's say, closed loop. Okay, and this is closed loop PI, and this is closed loop PID, and also the pair represented. Okay, now my dependent variables are my H and my AE are my dependent variables. Okay, now, and everything else can be parameters in this model. Okay, right, so now the classification of variables is done. So the next thing is to relate your dependent prime with your dependent variable. So the HCB1 is linked to the THCB1, and similarly the AE1 is linked with the TAE1. Okay, now, so I'm going to save it again, and now the variable value, let's say, so I will first, let's say, I'm gonna give values for an open loop. Let's say it's okay. I mean, even if you don't give, you can always change these values in ProCACD also. So I'm just gonna give it here. It's okay. So I've given the binary variable for the open loop. Let's say my inlet flow rate is 0.1 meter cube per hour. So, and the area is, let's say, 1 meter square. And you don't need to have a set point here, but yeah. And let's say my initial valve opening, which is alpha MV1, is 50%. Okay, now let's say I'm gonna save this one, and let's say I'm gonna run it just to see whether the model is correct or not. Okay, I haven't done the chat option, so I'm gonna go here. I'm gonna choose my variable as my alpha MV and followed by my control variable also. Then I'm gonna save it and I'm gonna run it and see how it works. Okay, so wait. So yeah, my valve opening is at 0.5, and this is my okay. This is the height. So it hasn't reached the steady state yet. So what I'm gonna do is I'm gonna further increase the time. Okay, let's say I'm gonna increase it by 10. So let's see if it has reached to the steady state value. Okay, now you can see that it has reached to a steady state value. So we're gonna use this one. So I'm gonna close this, click OK, and I'm gonna save this. And we don't need any MOT right now, so I'm going to close this. Now our generic model is pretty much ready. Now we will go to ProCACD, and then we'll see what things can be done using ProCACD. Okay, so this is the main interface of ProCACD, and you can see it's kind of tab structure representing different things what you can do. And the first and the foremost thing is, first you need to browse your model, and that's the tank model. And first we will again do the open loop and see if you select the open loop, it automatically disables other options which are related to your also. So I'm gonna choose this one, and the moment I choose this one, you could see that these are enabled for the user to select. But for this example, we only have one manipulated variable, which is alpha, and one control variable, which is height. So or else you could see okay, so and then you add, and this is your alpha MV1 and your HCV1, and this is your proportional integral. I mean, you can choose, by the way. So I'm going to choose PI. Okay, and now that I have defined the closed loop simulation, I'm going to go to the next step. Okay, so here it just shows you the model variables and the model characteristics, like how many parameters, how many known variables, how many explicit, and what are the manipulated variable and the control variables. You can see it here. And for example, if your system has multiple pairs of manipulated and control variables, it will give different color coordination so that it's easy to understand what are the parameters and variables representing which pair. Okay, so now I'm going to go to the next step of controller tuning. So here the controller tuning has 4 steps, and it will show and you have to do one by one in a sequential way. And once the instruction is completed, it will turn green. Okay, so now that it already has the number of periods, if you want you can change it, and it has the number of points. And now the third step, the first under the third step is generate data. So as I just said, first you need to do step input. You should give step changes and kind of record the system, how it responds, the response of the system. So I'm going to do that. So here what I'm going to do is I'm going to change the alpha MV1, and it already has some default. If you want to change the value, you're most welcome to change it, but I'm going to keep it these values. So the moment I click OK, it starts generating the data. So what it does is, like, it gives the step input, it runs the MOT behind, it will generate the data, and it will, at the end, once it's done, it will plot it for you, and you could see what is the step changes on the element and how the CV, or the height of the liquid in the tank changes. And if you want to see it on a combined plot, you could also do that. Okay, just 1 second. And now I have generated the data, and yeah, I'm going to close this one. The second step, you could see that the generate data tab has turned to green, so which means that it has fulfilled all the requirements for generation of the data. And the second one under step 3 is saving the data. So I'm satisfied with the data. So after looking at the step input and the response, I could see that it has gone to steady state at all the step changes. So I'm gonna save the data, and once I save it, you can see it has turned green. So now it is ready to kind of upload it to the online server of TimeGPID. So first of all, for this you should make sure that you have internet connection, or else it will fail. I mean, of course it will let you know that there is no proper internet connection, but yeah. And you can see, and if you have slow internet connection, it might take a while, because it has to kind of upload all the data, and if it has multiple set of MV and CV pairs, it will take more time. And once it uploads it, and the server will kind of read it and solve it, and it gives back the system identification results, like the transfer function data. And if you have multiple loops, for example, if you have different pairs of MV and CV, which is considered as one loop, for each and every loop the information is given, I mean the PID parameters and the system identification results. Now you can see that the PID is tuned, and you can click OK, and you can see I chose loop 1. Now we can see that I have got some results with respect to the proportionality constant and the integral constant, and you can see this represents the numerator and the denominator of the transfer function of the system. Okay, now that you have already got the controller parameters, now we should verify it whether the parameters are doing any good for our process or not. So how do you do that? So you should go to the closed loop run, and then, as I told, here there are different things you can do with respect to disturbance, or you can kind of change your set point and see how your process is kind of behaving with respect to the changes. Okay, so first I'm gonna do the disturbance. Okay, so I'm going to select the disturbance here, and I click parameter. Okay, here you can see the initial values, the f in the set point by proportional and integral constant. Now what I'm going to do is I'm going to increase my, there is a disturbance, let's say, in the flow rate, and it got let's say it has increased to 0.15. okay, now once you have kept the run, you can go, once you have set your values, you can go to run, okay, and click run here, and you can see that the process has started and it has completed. It's kind of very quick. So then you can go to plot, and you could see how the alpha changes, and also you could see the difference with respect to the control variable. Okay, you could see that it has overshot, and then since our set point is 3, it has come back really quick back to 3. So which means that the parameters are really working well with respect to disturbance rejection. Now if you want to look at how it works for set point tracking, we could also do that by just keeping the set point. So if you want, you can just go back to your original fin value, and then let's say now my set point is let's say 4. okay, so once I've defined my new set point, I'm going to click run here, and yeah, it's done. So I'll go to plot, and you could see how it has changed. It has initially overshot, and then it has come back to the new set point of 4. okay, and here you could actually do multiple runs also, so where you can select multiple runs, and you can say you can use the same input, which means that for each and every new run, it still considers the initial values as the beginning, and then it will see how the system behaves with respect to different parameters in each run. Or you can use continuous, which means this is the initial values, and in the run 1, whatever is the output will become the input for run 2. okay, now let's say we'll do a continuous one, and we'll say we want four runs, 4 multiple runs. okay, so what I'm gonna do here is, let's say in the beginning, in the first run, let's say I'm gonna do disturbance, I'm gonna give some disturbance in the feed flow rate. okay, and then in run 2, I'm gonna change, I'm gonna give, sorry, I've set the set point, right? So it has to be on the set point. So here what I'm gonna do is I'm gonna increase it to 4, and then again I'm gonna increase it to, let's say, 4.5, and I'm gonna reduce all the way to 2, and finally I'm gonna say what happens if I give my original set point, whether the system comes back to the original steady state or not. We will have to wait and see. okay, now that I've defined multiple runs, so I'm going to click run here. Now this will take a bit more time since it has to run 4 simulations in the background. okay, yeah, it's completed. Now let's plot and see. Now you could easily see how it is kind of changing. So in the first run, it is, so for each and every time interval we have given 10 seconds. So it has reached the steady state, the set point value of 4.2. okay, and then the first one was 4, the run 1, and the second run was 4.5, and suddenly we have reduced all the way to 2. And you could see that the system was responding really well, and it took pretty much very less time to actually come all the way from 4.5 to 2. And then finally we gave a value of 3 as a final set point, and it has reached the value. Okay, so you can see that the parameters, the control, the tuned parameters was very good, because it could really track the set point really well, and also you could see that it has rejected the disturbances and made sure that the control value is at the desired set point. Okay, so now this is done. Now I'm gonna show you other things which you can do in ProCACD. Okay, now what you can do is you can do a frequency analysis where you can kind of plot a Bode diagram. If you're not sure, that's okay. I mean, it's just that it produces the amplitude frequency diagram and the phase frequency. I'm gonna browse with parallel 3-tank system. Okay, so this is a bit complicated. Okay, there are 3 tanks in parallel. Okay, and all the 3 tanks has valves at the bottom. Okay, and also there is a side valve, and this, if you see, doesn't have any it is not connected to any controller, but these are valves. For example, if H1, or these are multi-dimensional valves, you can say, means if H1 is greater than H2, let's say, then the liquid will flow from tank 1 to tank 2. Okay, and similarly, if H2 is greater than H3, then the liquid will flow from from tank 2 to tank 3. And if the height H3 is greater than H2, then the liquid will flow from tank 3 to 2. Okay, now the idea, or the main objective here, is to kind of control the heights of the liquids in each and every tank. Okay, now let's see. Now I'll directly go to the closed loop. Now you could see there are 3 manipulated variables and control variables. So let's say I'm gonna choose one with 1, and the first one. See, all these 1s and 2s depends upon how you wrote your generic model. Okay, so when you're writing your generic model, be very sure which one you're looking. And of course, you can always link your MV1 with let's say CV2 and see how it's behaving. Okay, I mean, that's exactly why we have written the generic model too, and also given a lot of binary variables so that we could exhaust all the options and can get the best out of it. Okay, now, and here you could see that we have 3 sets, and all the color combinations are based upon each set. Okay, now I'm going to go directly to the controller tuning, and I'm going to generate the data. Okay, this will take a bit more time. You can see that there are 3 loops altogether representing for each page. Okay, now it's generating the data. Yeah, it will take more time. Yeah. Okay, it's almost done. Okay, so now we could see the different manipulated variables, and you could see the step changes is only on the first manipulated variable, which is alpha MV1, and similarly this is for the second step input on the second manipulated variable, and you can see how the h1 is changing. Okay, and it has a very little impact. The step change on MV1 has a very little impact on the other two heights, but it still has some impact, and it's the same case with the other ones also. But you could see that the step change on the second tank has a greater effect on tank 1 and 3, and similarly the valve or the valve on the tank 3 has very little effect on tank 1 and tank 2. So you need to understand that the valve on the second tank is kind of had a strong interactions with both the tanks, while tank 1 valve and tank 3 valve is has a very little effect on the other two tanks height. Okay, now I'm going to close this one. I'm going to save the data, and the data is saved. Now I'm going to send it to the system identification. So it will take slightly more time because it has 3 loops and data pertaining to all the step input changes for all the 3 loops. So just bear for some more time. Okay, it hasn't completed yet. Just 1 minute. So you need to have a good internet connection and also stable internet connection. If it loses connection between, then it will fail altogether. Okay, but anyway, we are trying to also include an offline method, like a text-based method, to kind of tune the PID parameters. Okay, so yeah, you can see that the PID parameters are now tuned, and if I choose loop 1, loop 2, loop 3, you could see different values. Okay, now I'm going to go to the close loop, and let's say, okay, I don't want to run the closed loop anyway. Here I only wanted you to show the RGA matrix. So now if you see, we have linked the first manipulated variable with the first control variable, and we have done all the analysis based upon that. Now we will use the transfer function from the system identification task, and we will kind of generate the relative gain matrix, and if the diagonal elements are close to 1, that will suggest that the pairing of those manipulated and control variables are better with respect to others, and the values which are close to 0.5 means they have strong interactions and you shouldn't be choosing them. Okay, so I have already clicked it. It will take a bit time since we have 3 loops here. Yeah. Okay, it's not yet done. So yeah, we need to still wait. So this tool is still under development. We would like to add more options to it, and also would like to change slightly the interface to to be more interactive with the user. And yeah, this is just the work of one master student who worked on this project for, let's say, 6 to 8 months mostly, or less than a year. Okay, and we would of course we would like to continue working on this and kind of expand it to other avenues, because there are other different problems which can be which can be solved. So we would also would like to under controls and all these things. So we would like to have all those kind of capabilities in this kind of platform, and to make this tool as a kind of an to-go tool for any control or design related problems. Okay, so it's taking more time. Just hold on for a second. By the way, this tool was developed completely in C#. Okay, and some elements are kind of hidden right now because we are kind of testing it, like the integrated design and control options, where we also added an optimizer section. I explained you the solution approach for the integrated control and design in the lecture, right? The last two slides. So we actually also implemented that, but we are not showing it right now because that's still in the testing phase. Okay. And yeah, if you are using this tool, or if you're interested in kind of working on these kind of tools, or developing or expanding the scope of this tool, I mean, you can always contact us. Okay, and we could probably formulate a project and you can see how we can do this. Okay. Oh, it's taking more time. I mean, yeah, at times, I mean, yeah, so this is how it you should be doing. I mean, if you have multiple loops and kind of thing, you just need to come here after you have tuned the controller. Once the transfer function information is present, that is exactly what the relative gain matrix will use to generate the array. So it uses the transfer functions of all the three loops, and then it will try to calculate the relative gains, and then it will show the result to you. Okay, so we'll just wait for another 30 seconds, and if not, we can close this here. Okay. As I said, I mean, if you have any questions, even with MBOT in solving your assignment problems, you could always write to me. There were some students who has written to me asking me about few questions in that, and I'm very happy that they are kind of able to write and kind of use MBOT to do the assignments. Okay. So yeah, I think we will stop the lecture here. So okay, all right then. Thank you.